In this video, we talk about invariants of a second order tensor, deviatoric tensor, and vector calculus. Let A be a second order tensor with components aij with in the coordinate system with basis vector ei, and the components a bar aij in the coordinate system with basis vector e bar i. E bar. So E bar I is related to E bar E through an orthogonal matrix M. Suppose lambda is an eigenvalue of A bar, so it means it satisfies the characteristic equation which comes from determinant of A bar minus lambda I equal to 0. So then A bar is related to A through the orthogonal matrix. In expression it is M transpose. So therefore in this determinant expression, in place of A bar we write M transpose. So we can take out M and M transpose, and a determinant of A, B, C is always equal to determinant of A, determinant of B, and determinant of C. So we can write that expression of determinant and in terms of products. Since M is an orthogonal matrix, determinant of M is 1. So therefore we get back to determinant of A minus lambda equal to 0. It means lambda is an eigenvalue for A also, right? So thus the eigenvalues are invariant under coordinate transformation. Suppose A is symmetric, A1, A2, A3 are the eigenvalues, x1, x2, x3 are the normalized eigenvectors, then construct a matrix P transpose as the column wise they are the eigenvectors of the A, and when we find A bar with transform like P transpose, then you get the eigenvalues along the diagonal. So there exists a coordinate system in which the matrix of a symmetric second order tensor is a diagonal where the components are the eigenvalues. Let's say if A1 is equal to A2 and A3 is different from A1 and A2, then vector only x3 is uniquely determined. The x1 and x2 may be any two vectors which are orthogonal to each other and also to x3. Let's say A1, A2, A3 all of them are equal together, then the eigenvectors can be any three mutually orthogonal directions, and the A will be the spherical tensor which is invariant under any coordinate in any coordinate system. The components will be the same. So in many applications, different invariants can be chosen rather than the eigenvalues only. So one can choose a symmetric functions like sum of the eigenvalue, squares of the sum of the squares of the eigenvalue, sum of the cube third power of the eigenvalues. So all these sets can be symmetric functions can be written as trace of A square and trace of A cube. So another set one can choose is I1, which is sum of the eigenvalues, I2 in this form of the product, and I3 is the product of the eigenvalues. This is nothing but determinant of A. So we can express I1 as trace of A, I2 as half of trace of A whole square minus trace of A square, and I3 as determinant of A. So these three coefficients I1, these three invariants comes as the coefficients in the characteristic equation of in Cayley-Hamilton theorem. So Cayley-Hamilton theorem, in place of the characteristic equation we can replace by the matrices, and the coefficients are given by these invariants. So what is deviatoric tensor? A tensor of this form which has a property that its trace is 0. So you make the trace of A multiplied with the identity, since it is second order, so we take it 1 by 3. Then this matrix has trace 0. So a tensor whose trace is 0 is called deviatoric tensor. A prime is a deviator of A. A tensor can be decomposed as the sum of its deviator and a spherical tensor. Spherical tensor is this identity matrix with a coefficient. So the two non-zero invariants of A prime, they are written, they get this because the trace is 0, I1 prime is 0. So we'll have only I2 prime and I3 prime. So after some manipulation, one can obtain I2 prime and I3 prime in terms of I1, I2 and I3 only. So this is how we deviatoric tensors are represented. The invariants corresponding to deviatoric tensor takes the form. So it's a simple recollection of what we know in vector calculus, how to write a gradient of a scalar function, and the definition of the gradient of a scalar function, definition of a divergent of a vector, definition of a curl of a vector, and this is the Gauss theorem. So the divergence of the vector in a volume is defined, it can be calculated through defining the vector on the surfaces. There is one more theorem, it's a Stokes theorem. Curl of a vector on a surface is given by the vector along the boundaries of the surface. It can be calculated by the vectors on the boundaries of the surface. That is the Stokes theorem. So these are the necessary mathematics required, and we'll see from the next video regarding the body's configurations and kinematics. Thank you.